In this video, we're going to go over part A from the mock exam for the final for Linear Algebra 2, MATB24. The first two questions are asking us whether or not it's a linear transformation. So here, this is more about recognizing what type of linear transformations, what expressions are linear and which ones are not. So with linear, what we'll have is we'll have a linear combination of each variable in each spot. Okay. Here we have a product. Whenever you see a product like this, that is pretty close to saying, hey, it's not linear. Now, here, if you're not sure, you can always go through and check. So you can always do T of x1, x2 plus y1, y2 equals T of x1 plus y1, x2 plus y2 equals x1 plus y1 minus x2 plus y2, comma, minus x2 plus y2, which when we expand gives us x1 minus x2 minus x2 plus y1 minus y2 minus y2, which equals T of x1, x2 plus T of y1, y2. And you can check your scaling, but this is in fact true. We are a linear operator. Okay. Now, what's careful here is I use the term operator. Remember, operator means we need to take from and go to the same set. So I could change this question slightly where my output was x1 minus x2 minus x2, and this would now be false because it goes from R2 to R3. But here we go from R2 to R2. Now, in A2, here, because we have this product, this is false. This is not a linear transformation, thus it's not a linear operator. And here, if you were to prove that it was false, you'd provide a counterexample of some kind. I'm thinking T of 1, 0, plus T of 0, 1 compared to T of 1, 1. This equals 0, 0 plus 0 minus 1, whereas this equals 1 minus 1. And those are not equal to each other. Okay. Remember, with a counterexample, be specific. Now, one of these operators is linear. For the operator is linear, compute the matrix representation in the standard basis. Well, that's asking what does T do to 1, 0? For a 1, this is going to be 1 minus 1, which implies that T of E1 in the standard basis beta is going to be 1 minus 1, and T of 0, 1 equals minus 1 minus 1. Oh, this should be 1, 0, so this is a 1, 0. This is a minus 1 minus 1, which implies that T of E2 in the standard basis is going to be minus 1 minus 1, meaning that the matrix representation of T in the standard basis beta is going to be 1, 0, minus 1 minus 1. A4. If W1 and W2 are two subsets of a finite dimensional vector space that are orthogonal to each other, what condition must be met for the sum of them to equal V? Well, because they're orthogonal, we know that they're going to be independent. They're going to be linearly independent from each other. So because of that, what we need is we need that W1 plus W2 equals V. That's one of the important, that it is a sum. It forms V. Then another condition that we could have is the dimension of W1 plus the dimension of W2 equals V. you might be thinking, well, W1, the intersection of W1 and W2 equals 0, but that comes from orthogonality. So this is not one of the conditions. The big thing that we want to make sure is that we somehow get this summing up to V. Because they are orthogonal sets, they're going to be linearly independent, which means they're going to form a direct sum. But we need to make sure that it forms a direct sum equaling to V. Now, here, divide a self-adjoint matrix that is not unitary. The big thing here, self-adjoint, means that it equals its own transpose. So I'm just going to do 2, 2, 0, 0. This is self-adjoint. It equals its own complex conjugate, but it's not unitary. Um, the rows and columns aren't unitary. So that's kind of what I'm want with these types of questions, or the way that I like to think for these types of questions. So I come up with something that's obviously self-adjoint and obviously not unitary. I don't want to come up with a clever, sneaky example, just as obvious as it possibly can be. Next, we have a linear operator and a characteristic polynomial. What are the dimensions of the null space? Here, the idea is that given the characteristic polynomial, that null space is the dimension of the eigenspaces. So if we look at e minus 3 cubed, this is what I'm looking at. And the dimension of that subspace, when we do the primary decomposition, this dimension is going to be 3. And we know from linear algebra 1 that the characteristic space is bounded at most 3 and at least 1. So if I'm looking at those dimensions, this tells me the upper bound for the dimension of that space, and the lower bound for the dimension of that space is going to be 1. So the dimension for this space of the null space of t minus 2i is somewhere in the set of 1, 2, or 3. So 1, 2, or 3 vectors are going to be within that null space. If we let E be a non-zero projection and f of x equal this set of vectors, what are the eigenvalues for E? So if I have a non-zero projection, that means I am diagonalizable. And the spectrum of E equals the set 0 and 1, or the set 1. I never said that I was a non-identity projection. So the zero projection is the zero operator. The identity projection is the identity operator. And then there's non-zero, means not this one, but could be this one, maybe. Non-identity could be the zero, and non-zero non-identity would mean that it's not the identity operator and it's not the zero operator, meaning it has to have both eigenvalues 1 and 0. But because of this, we know it's diagonalizable, which means that we know it's upper triangular, meaning that f of sigma of E is equal to sigma f of E, which equals the set of f of lambda, where lambda is in sigma of E. So what I'm doing is I'm just going to apply this polynomial to both of these sets. So f of 0 equals 3 times 0 squared minus 2, which equals 0 minus 2, which equals minus 2. And f of 1 equals 3 times 1 squared minus 2, which equals 3 minus 2, which equals 1. So my sets would be minus 2, 1, or 1. Because I don't know which one of the sets is the original one for E. It could be both. Now, in the exam situation, we probably give you credit for this one here if you didn't include this one, but I wanted to give you an option where it wasn't necessarily both. Now, in number 8, we look at a example of a possible 4x4 matrix with this expression given that it's not normal. Now, because it's not normal, that means it doesn't commute with its adjoint. It doesn't have that it's not diagonalizable. So with that, what we're looking for is we're looking for one Jordan block. 1, 3, 4, 1, 4 is a fine example. But it could be a Jordan block with 1, a Jordan block with 2, a Jordan block with 3. It could be any of those. So the eigenvalues are 1, 3, and 4. So that's what I put on the diagonal. And then it's not diagonalized, or it's not normal, which we're going to take as not diagonalizable. It doesn't commute with its adjoint. Okay. Now, if we have A9, if we have a sigma A with these entries, A is diagonalizable, define a polynomial f of x such that f of A is a non-zero projection. So instead of going from 0 and 1 to other values, we're going to be mapping the numbers, the set 1, 3, 5. We want to map it to 0 and 1. And the easiest way to do non-zero projection is to make sure some of the numbers map to 0 and some of the numbers map to 1. Now, you could come up with your own polynomial and try to figure it out. You could think, okay, I'm going to make x minus 1 and x minus 3. F of x equals this, so that both 1 and 3 go to 0. And now I need to find some constant that makes when I plug in 5, I get, when I plug in 5, I get 1. So 5 minus 1 times 5 minus 3 equals 4 times 2 equals 8. So I'm going to put a function 1/8 out front. But if we look at this, this is the Lagrange polynomial. So yes, we can figure it out without using the Lagrange polynomial, but often the Lagrange polynomial will help us come up with this problem quite easily. Remember, it produces projections. So this is a valid f of x. And any of those Lagrange polynomials would work. And finally, we're looking at the matrix here over Z mod 2. Now, the first thing that I notice when I look at this is I notice a companion matrix. Has that nice subdiagonal form, meaning that these are my coefficients. So I have x cubed plus 0x plus negative 1x plus 0. Now this negative 1 is the additive inverse of 1 in Z mod 2. So this equals x cubed plus x, which equals x squared plus 1. The question is, does this factor? Well, when I look at x squared plus 1 to determine if it factors, I'm going to use the fundamental remainder theorem. So if I plug in 1, I get 1 plus 1, which equals 2, which equals 0. So yes, f of 1 is a root, meaning I can factor by x plus negative 1, or x plus 1, because I'm dealing with the Z mod 2. X squared plus 0x plus 1 goes in one time, x squared plus x. Remember, subtracting is adding the additive inverse. So it becomes 0x squared. This becomes plus x plus 1. This is x plus 1. So x plus 1 gives me 0. So my polynomial is x plus 1, x plus 1. Now, Yes, it's a product of linear factors, but it's not a product of distinct linear factors. The minimal polynomial is x plus 1, x plus 1, or x plus 1 squared, which is not a product of distinct linear factors. Therefore, no, we are not diagonalizable.